if we have a nonlinear function like sine, and we want to approximate it with a line, and call that a linear function, or the linearization, or the tangent line for that graph, then we can use this idea of the differential, because the change in output is going to be approximately equal to the slope times the change in input. Of course, the slope we want to use is the derivative of our function at our point of interest, right, times the change in x. So we'll just look at how much does y change from its initial value. That's going to be, for the linearization, it's actually going to be the value of the slope at our center point, or the point where we're near. In this case, we're saying x is near 0, but in general it would be some value x naught. And then this is the change in x. How far does x move away from x naught? Now, in our particular case, the function is the sine of x, so the derivative is the cosine, and the derivative at our particular value, in this case x naught is 0, so that would be the cosine of 0, which is 1. We also need a point on the graph where we need this x naught, y naught, right? Well, we know that when x is 0, the sine of 0 is 0, so we have to find the line with this slope that goes through this point. So the change in y would be y minus the initial y value is equal to the slope, which is 1, times x minus the initial x value. So we get the line, in this case, y equals x. Just so you can see what's happening here, let's look at the graph of sine. And what we did is we said we want to find the best line that approximates the function near that point 0, 0. And we found, by using the derivative to find the slope, and then using that idea that the change in output is slope times change in input, we got the equation of the line as y equals x. That line is the best linear function that approximates this nonlinear sine function near 0. You can see it's a really pretty good approximation, as long as you don't go too far to the right or left of an input of 0. Let's do another example. This time, let's do it near the point where x equals pi. Again, we have this basic idea that the change in y is approximately the slope times the change in x. And again, our function is sine of x, so the derivative of our function is cosine of x. And that gives us the slope of the function if we plug in a particular x value. If we plug in the value pi, the slope is the cosine of pi, and the cosine of pi, you'll recall, is -1. We also need a point on the line. We know that when you plug in pi, the sine of pi is 0. So this gives me my x naught and my y naught. So the change in y, that would be y minus its initial value, is equal to the slope, which is -1, times x minus its initial value. So we get this linear function, y equals -x, -1 times -pi would make plus pi. There's the linearization that works near x equals pi. Let's graph that one too, so you can see the relationship here. This time we got -x plus pi, so I'll put that in. And you can see we get a different line. Now this line isn't very good when x is near 0, but it's really good when x is near pi. So we've got a linearization that works well near the value of pi, as long as we don't go too far to the left or right of pi. The pink line is a great approximation for the yellow line.